All right, guys, now we're going to talk about collision theory. So a lot of these, so this chapter is going to seem a little disjointed, but we're trying to just fill in a whole bunch of gaps about kind of the details of how reactions work. So now we're going to actually get into the nitty-gritty of how reactions work and why they work and what they do and the energy and how the speed of them and all these things. So we have to start with what seems like a pretty simple idea. And this is collision theory. Now, collision theory, it's one of those it's so simple that it's kind of duh, but when you think about the you never realize what all the implications are until you think about it. So collision theory is this. It's a set of statements that talk about what has to happen for a reaction to happen. So here's one of them, and this is the sort of duh thing, but there's a lot of things that come out of this that are really important. Reactant particles, in order for reactants to react, they have to collide with each other. They have to touch. They have to come into contact with each other, right? So, I mean, this explains a number of things. Like, for example, why we want to break, if you want something to react, you break it up or you mix it in, right? Because if you have just a block of particles, only the ones on the outside can react at all. So like when iron rusts, it's just the outside part that rusts, right? So, and it's not till that flakes off that more underneath it can rust. The next is colliding particles, right? Just running into each other isn't enough, right? Just running into each other doesn't do it. They have to have a minimum energy. They have to hit with enough energy to make the reaction. Because the fact that the compound exists as it is before the reaction happens, the fact that it exists at all means it must be somewhat stable, right? Otherwise it wouldn't exist. So you have to sort of hit them enough to disrupt that already somewhat stable situation. Colliding particles have to have the proper orientation, right? So in order for, how do I say this? I have a better example that's already drawn out. So they have to collide in the right orientation. They have to, the right part of the molecule has to hit the right part of the other molecule. So starting kind of from that first tenet, reactions take place most readily when reactant particles are free to move around. So gas, liquid, or aqueous. Solid reactions are real slow, even solids with gases. This is why very commonly ionic compounds, which are normally these solid salts, when you see them in reactions, you'll see them as aqueous, right? They're dissolved. They can move around more easily. They can collide with other reactants much more easily than if they were solid, right? Okay, solid reactants only happen at the surface. However, if I did have a solid that I was trying to get to react, breaking it up into smaller bits to expose more surface area helps. Okay, that's that first thing. They have to collide, they have to touch in order to react. Okay, so the state of matter matters. Activation energy. This has to do with the second tenet. They have to have enough energy. And the reason they have to have enough energy is imagine that, so I'm going to do this thing called a reaction diagram. So this is the reaction progress. So over here you have reactants and you have products. So what happens is you have energy here. So the reactants have a certain energy and the products have a certain energy, and we'll talk about their relative energies in a bit. Right now what I want to talk about is the fact that in order to get from here to there, the reactants have to collide and go through some really weird intermediate contortions. I mean, granted, this happens over the course of femtoseconds, where they move through these really unstable, really crazy configurations, right? In order for, should be an extra S there. Simply put, for an acid, as simple as something for an acid, in order for a proton to go from here to there, you have to go through a moment of time where you have this situation, right, which is really unstable, But at the end of the whole thing, it pays off because you get this and you go back to a very stable configuration. But in the moment in between, it's really not comfortable for the atom for the molecules to do. So that represents this giant increase in energy to get over the bump, right? This energy is what we call the activation energy, EA. So that's why reactions or reactants have to collide with a certain amount of energy, because that energy comes from the kinetic energy of the particles colliding, and that the more kinetic energy those particles have, the more energy that can be put towards the reaction, and then they can get over it. If they don't have enough energy, they go up and fall back down. They can't do it. They can't get over the hill, right? So here's an example. If you think about it, why do you have to strike a match? Why don't matches just burst into flames, right? Because the phosphorus in a match head is very stable as it is. Well, somewhat stable. But striking it, that friction, right? You're increasing the kinetic energy just enough for some of the particles to get over the bump. And when they get over the bump, they start producing more heat, and that cascades, that chains to the molecules next to them, and next to them, and next to them. And that goes over and that's how we get over the activation energy. Most of the things around us are flammable. Tables, chairs, wood, pencils, papers, books, or the clothes we're wearing, right? Activation energy is what explains why all those things are not on fire right now, right? So it's important. And it makes sense, right? You know that they can catch fire, but they don't always. They're not constantly on fire. And so the activation energy is the minimum combined kinetic energy that colliding particles have to get over that bump and make the reaction occur. Different reactions have different activation energies. It depends. Some reactions are easier to happen. So in a slow reaction, the activation energy is far above the kinetic energy of the molecules. In other words, the activation energy is really high. One of the reasons a reaction can be very slow is because not many of the particles have enough energy to collide, right? If you have a fast reaction, it's because they're colliding all the time. They're colliding with enough energy all the time. So some reactions, anyway, lighting a match, there we go. Orientation. Now this one's a little weird. The upshots of this aren't as obvious. But here, let's say we're reacting something to make, we have BRNO, and we're reacting to make NO, two nitrogen monoxide molecules, and two bromine molecules. Well, if they collide this way, great. If they collide this way, great. But if they collide in such a way as that the bromine atoms can't touch, well, that's no dice. So this explains why there are always going to be, this is why no reaction, even if you heat it up enough, happens instantaneously, right? Because there are always going to be some collisions that have enough kinetic energy, but hit with the wrong orientation to react. They're just not going to react. They've got to hit the right way. Okay. Next thing, exothermic, endothermic. Now we talked about exothermic, endothermic when we talked about changes of state, right? Going from, like when we're talking about boiling and melting. So remember, exothermic, so we're going to talk about exothermic reactions as opposed to exothermic changes of state. Exothermic reaction is a reaction where energy is released, right? Energy is released as the reaction occurs. Endothermic means energy is required, taken in as a whole. This is not the activation energy, because there's that bump in the activation energy. You can get the energy back. It's just, you have to have that minimum. It's kind of the minimum for entry. So what makes a reaction exothermic or endothermic, if not the activation energy? It has to do with the bonds. When you rearrange something, you're breaking bonds. Breaking bonds always takes energy. You have to put energy to break those bonds. They're stable. But you're going to make new bonds at the end of the whole thing. So let me explain. let's talk about this. I'm going to do two of these reaction diagrams. Energy, energy. That wasn't really dramatic enough. So this is reactants, this is products, reactants, products. This is the activation energy is the distance from here to here, right? Activation energy is from here to here. But see, here's the thing. This is very stable. I've got to put a lot of energy into this reaction to break it apart. And it's still kind of high energy. It's not super stable. So I put in a lot of energy to get up to here, right? From here to here, I put in a lot of energy. But when the reaction actually completes, I don't get all of it back, right? I get less energy out than I put in. This is an endothermic reaction, right? The bonds at the end of making those bonds at the end don't give back as much energy as I needed to break the bonds at the beginning. The opposite here is true, right? I get back more energy, right, than I had to put in. So this is exothermic, right? The difference here, the difference in this energy, this is how much energy I get back, this is how much energy I have to put in, right? So this balance between the broken and new bonds dictate whether it's exothermic or endothermic. Energy to break bonds, if it's more than the energy you get back that is released, it's endothermic. You put in more than you got out in the net aggregate. When you get back more than you put in, that's exothermic, right? And this doesn't have any bearing on how big the activation energy is, right? The activation energy is just how much you got to pay to play, how much energy the collisions have to have. And then exothermic, endothermic is based on the bonds. The degree of the activation energy is how weirdly contorted the intermediate is. So that's so there's reactants, products, and this thing, this high energy thing here is called the intermediate. So there you go.